Okay. So, welcome you all to take part in the sixth Gauge Gravity talk of the season two. So, this is an online seminar series which focuses broadly on diverse topics in gauge gravity theories. And the seminars are held roughly once a month, preferably Wednesday. And these talks are recorded and we upload it on the CHAP YouTube channel. So there's some instruction for the audience. So audience, they will be muted during the talk, and however, the members can ask question by raising their hands. Urgent question, if there are any, like they can be posted in the chat box, which we will communicate to the moderator, or just maybe if there is a very exciting this thing, so we can just gets involved in a discussion also. So today's speaker is Suvendu Giri. He is from Uppsala University from Sweden. He did his PhD from Uppsala University under Ulf Danielsson, and thereafter he was a postdoc at Milan, and followed by Princeton, and followed by Perimeter. And so he's currently based in Uppsala University, where he has got some grant to pursue his research interest on black hole mimickers. So his talk today will be on black hole mimickers, why they matter, and where we stand. So, Sovendu, yeah, over to you, basically. So I will mute myself now.
Right. Thank you very much. Uh, you see my screen?
Yeah, yeah.
Okay, perfect. All right. So thank you very much for the invitation. I'm very happy to talk about this. In the next roughly an hour, I will try to tell you about this one problem that I've been thinking about quite a lot for the past few years. So they're called black hole mimickers. I'll explain as we go what they are. So again, this is not a definitive talk where you will go back with all the answers. This is more of a discussion where I'll tell you the state of the field, why this is interesting to me, and perhaps it's also interesting to you, how far we have come, like as a community, to answering these questions, and in my opinion, what are the outstanding questions that we should answer. Okay, so let me begin by essentially, okay, so the talk is about black hole mimicker. So let me start by motivating why this is an important problem. So the story of black holes actually goes back before Schwarzschild, contrary to how many of us learn about black holes. So people were thinking about black holes already in Newtonian gravity in the late 1700s, where the idea was that if you have a object which is dense and heavy, so it's dense enough that not even light can escape. So this is the thing that you learn about in high school. Like a black hole is something that escape velocity is equal to the speed of light. So people are thinking about this already in the 1700s, and John Michell, who is an Englishman, he called them dark stars. So this is the origin of the concept of a black hole. And then after Einstein wrote down his theory, famously Carl Schwarzschild came up with a solution very quickly, which kind of satisfied this criteria. So this was still not called a black hole. It was still called a Schwarzschild solution or a Schwarzschild singularity. And then, as you very well know, about 50 years later, Roy Kerr came up with his celebrated solution where he constructed something which rotates and has similar properties. So this was still not called a black hole. It was still called a rotate or a Kerr singularity or a Kerr solution. So the name black hole is actually attributed to Robert Dicke and then John Wheeler, who popularized it. So these were both professors at Princeton University. So Robert Dicke knew about this curious incident which happened in India in the late 1700s. So this is when Nawab Shirazuddaulah was ruling West Bengal. And then during the British invasion, he sieged a bunch of prisoners of war and put them in a dungeon in what was then Fort William at that time. Unfortunately, this was a very unfortunate event. There were 100 some people, and then most of them died overnight because it was a cramped dungeon. So this came to be known as the Black Hole of Calcutta. And if you go to Calcutta, you can still see plaques dating back way before Schwarzschild wrote his solution, and you see the word black hole appear there. So Robert Dicke was aware of this, and apparently, whenever somebody would lose a pencil or something in his household, he would say, "Oh, the black hole took it away." So John Wheeler heard this phrase over and over, and then when he was confronted by a journalist about this solution, talking about Kerr solutions, then he was like, "Oh, it's like the black hole." And to my knowledge, that's the origin when people started calling these solutions as black hole solutions. So it's black holes are a very black holes are from India. That's how I would like to think, which is a very good thing. Uh, anyway, so right, so up to this point, black holes were these mathematical curiosities. You had these singular solutions which had some properties, etc. But then the question is, are these real things that you should expect to exist in nature, or are these just mathematical curiosities that people have written down? So the first solution, which or the first object in the sky, which kind of looked like it could be one of these solutions, was something which was discovered in the constellation of Cygnus. So this is a simulation of the night sky as seen from India, uh, roughly at this time of the year. So yeah, if you take a moderately sized telescope and you point there, you'll see a magnitude 15, like very dim star, and that's roughly the location of Cygnus X1, which is the first stellar mass black hole that was discovered in the night sky. So this is an X-ray binary, as in we think there's a black hole, and then there is a star which is being accreted into the black hole, and in the process it's emitting X-rays. And if you turn on X-ray, like your X-ray telescopes, you will see X-ray emissions. So this is the first stellar mass black hole that was seen. But then there's another category of black holes, which are supermassive black holes. It's a different family. And the first one, or one of the best studied ones in that category is the one that sits at the center of our galaxy. So this is Sagittarius A star. Again, if you're lucky to have low light pollution and you look into the constellation of Sagittarius, here is roughly where you would see it. And this is the picture which shows the orbits of the closest 8 stars that are orbiting the galactic center. So right here if you look at all of these elliptical orbits, you see that it looks like they're going around a common center, which you don't see in this picture. So that would be kind of where my mouse is pointing. That's where you should imagine the black hole at the center of our galaxy to be, and that's Sagittarius A star. Right. So once these things started happening, it was kind of obvious that, okay, there is something sitting there which is massive enough that it's causing all of these stars to go around it, but we don't see it. So it cannot be a big star. Also, if you then look at how close the orbits of these stars are approaching it, you can see that it cannot be a very big object because the star is getting very close. So from here, I think the limits are of the order of 1,000 RG, of 1,000 gravitational radii, and so on. And then using further observations, you can kind of narrow it down to tens of RG. So then you say, okay, it's either something like a neutron star or something else. But then if you work out astrophysics, you realize that neutron stars cannot be so heavy. And then the obvious conclusion is, okay, it must be a black hole, because what else could it be? Right. So that's kind of the indirect evidence we have had for the existence of black holes. And by now we are convinced, okay, sure, black holes must exist in nature. But now we live in this era of gravitational wave astrophysics where things have changed. We don't have to rely on indirect observations. We can do more direct tests of things. So again, the celebrated event, which happened 10 years ago, and this year there are celebrations everywhere around the world, also in India. I think there was a recent one in Gandhinagar, from what I know, etc. So this is again the famous detection of gravitational waves by the LIGO detector. So these are the two detectors, one on the east coast, one on the west coast of the US, separated by a few thousand kilometers. These, as you may very well know, are interferometers. They're L-shaped. These are like Michelson interferometers, except they're using laser lights. And then when a gravitational wave passes through, the arms of the lasers get squeezed differently, and then you can see interference patterns, which tell you that you've seen a gravitational wave. And then by using two of them, you can find out better things than if you just had one. You can localize them in the sky. You can get some polarization information, et cetera, et cetera. So this got the Nobel Prize, and then these are the famous waveforms compared to the numerical waveforms and the residuals and the chirps, etc. So all of this is to say that we don't just have to rely on optical, X-ray, etc. observations. We also have a different channel now, which is a gravitational wave channel, and this is somehow superior in the sense that you can probe strong field effects. Right? You're not just looking at things which are 10 RG or 1,000 RG away from it. You're actually looking at things where the horizons are kind of touching each other. That's the merger phase. Right? So if we can be clever enough to understand what to expect for a black hole and not a black hole, then we should be able to discriminate using these waveforms. Is what we are seeing a black hole, or is it something else? Okay, in a even better turn of events for humanity, we have even another channel which has also opened up in the last few years, which is electromagnetic interferometer experiments. So these are called VLBI experiments using radio waves. In particular, there's a network of telescopes called the Event Horizon Telescope. So these are many telescopes spread out all over the world. And then using a combination of these, you can kind of build interferometers. So they are not real interferometers, but you can just take observations spread out over multiple sites, and then you can correlate them to kind of do interferometry. And this has given us these fantastic images that you have probably all seen. Okay, you might have seen them without these weird looking lines. So the weird looking lines are just magnetic field polarization, which have been now added in the new data. In the previous ones, you might just have seen blobs. So this is supposed to be a direct image of how a black hole would look if you would just look at it. Right. So it's not really that, but this is the idea, that this is what it's supposed to be. So all of this is to say that in today's world, we have many, many different ways of probing what a very, very compact object is supposed to be. The only requirement is we have to be clever enough to distinguish if it's a black hole or not a black hole. How should these images, these waveforms, these observations differ? And if we can kind of get to that point, then we have discriminatory power to understand, is what we are looking at a black hole or not a black hole? So far, I have been arguing in favor of black holes, essentially telling you that, okay, if it's not a neutron star, but it's heavier and denser, then pretty much GR kind of forces you to think it's a black hole. Fine. But then, like you might have expected from the title of my talk, I'm going to talk about black hole mimickers, not black holes. So then the question is, okay, why would you even question this paradigm that black holes exist? I mean, clearly it's a good paradigm. So let me try to motivate to you, at least from my side, why I think this is a valid question to ask and why I am interested in this problem. So observationally, what I've showed you so far is gravitational waves and electromagnetic data are consistent with observations being black holes. But as I've been trying to sneakily allude, you don't really probe horizons using all of this, right? You are still far enough away from the horizon if you're doing direct observations, also electromagnetic. Gravitational waves can get you so close, but there are fundamental issues with things, which I'll explain in a second, which give you pause to think that maybe there could be other things. Also, if you're just a data-driven person, you might say, okay, if I'm completely agnostic to any kind of theory or any kind of problems that might pop up, is it exclusive that the observations tell me we have black holes? And the answer is no, they're not exclusive. There are error bars, and the error bars essentially, could sway you either way. But then the question is, okay, theoretically, does it even make sense to think of non-black holes? Like, is there a problem with black holes? And the answer is obviously there is a problem with black holes. So as an example, let's consider a curved black hole. These are completely regular and smooth solutions outside the horizon. We're all happy with that. But then if you look inside, there are problems. So you have an inner horizon, which is a Cauchy horizon, and these are typically problematic in physics. So you can write, if you think of Einstein's equations as a set of second-order PDEs, partial differential equations, so you can set this whole thing up as a Cauchy problem, right? So you give some initial data, you want to evolve it, you want to see what happens. The inner horizon of curved black holes are a Cauchy horizon, meaning that you cannot evolve your data past it. So you really have no predictive power to tell me what's going on inside. So this is a problem if you think of it in the following way. You have a solution that you have constructed in GR, right? So GR is a low energy theory, as in it's not supposed to be valid if you crank up your energy, let's say, all the way to the Planck scale. Even in the purview of this theory, there is a region of space-time which you don't really, which is not really covered by your theory, right? For example, if you hit the singularity, clearly you don't expect GR to be valid. And then the usual expectation is that, yeah, quantum gravity will tell you what is going on, but quantum gravity is just a proxy for whatever is going to happen at small scales, right? You don't have to subscribe to any particular theory of quantum gravity, but any theory that is going to tell me how gravity behaves at small scale should be able to get rid of the singularity and explain what is going on, how do I evolve past these things? So as soon as you hit this point, you realize, okay, GR is an effective solution, is an effective theory good at low energies, but at high energy, something is going to happen. Then you say, okay, what is that something? Is that something still going to give me a black hole if I look at high enough energy, or is it going to change things? So if you're a particle physicist, one way to think about this would be a 4-point interaction, right? So if you had a 4-point interaction, you would have, initially, before people resolved it, there was this confusion. Well, there's a 4-point interaction. What's going on? But then he said, no. If you actually have high enough energies, it's just 2-3-point interactions, and everything is fine. So the question is, could something similar happen with black holes? What we think of as a black hole from far away maybe is still a valid, effective solution. But as you really get close, maybe things are changing inside. And the question is, are they changing? How do you find out? And what is the effect of that change? In a similar spirit, you you may very well know that interior solution for a curved black hole has not been, we don't have a good interior solution which can connect smoothly with the exterior. So that this just goes in the same direction. On the other hand, if you think about black hole thermodynamics and start thinking more on those lines, then there are also, famously, there are problems. For instance, Bekenstein and Hawking showed that black hole thermodynamics, so black holes are thermodynamical objects. They have entropy, which have a thermodynamic interpretation. In particular, black hole entropy is just its area in Planck units. So if you have, let's say, a macroscopic black hole, a solar mass black hole, etc., this S is a very, very large number. It's just the macroscopic area in Planck units. So it's a very big number. But if it's a thermodynamic entropy, then the expectation is that there should be states. You can count these microstates. And then the number of microstates should somehow give you what this entropy is. But then if you have a large entropy, then the expectation is from thermodynamics, you have a large number of microstates over which this entropy is distributed. But then GR tells you, no, no, you have a no-hair theorem. You know, a black hole is unique. I mean, it doesn't matter if you form a black hole with by throwing a television into your black hole, or you throw a book into a black hole, or I jump in. It doesn't matter what falls in. All that matters is what was the mass of the object, what is the spin, and what is the charge. It doesn't care about the microscopic things that made it up. So then you say, okay, if I give you these three numbers, there is exactly one such black hole in my universe. Every such black hole is alike. So there are no microstates. And then the question is, okay, how do you reconcile these things? And again, the expectation is that quantum gravity should tell us, right? That somehow this has to be resolved by quantum gravity. So you can keep thinking further, and then these are like very well-known problems which people have wondered about for decades and are still wondering about. There is also the black hole information puzzle in a very similar spirit. If you throw information into a black hole and the black hole evaporates at some point of time, what happened to the information? So a cartoon version or an easy version to explain is if you throw a pure state into the black hole, once one of the partners evaporates away, you are left with the mixed state, and this violates unitarity. So there are many ways to resolve this. Essentially, you can say, okay, if you want to resolve this problem, you need something where the information that you have thrown in is somehow stored on the horizon so that it can evaporate away with Hawking radiation, but it should also fall into the horizon because clearly the horizon is not a special place. And then there are different ways that people have tried to resolve it. There are ongoing efforts. There is no clear resolution. Some resolutions are closer to the answer than the others, etc. But the point I'm trying to make is we don't know for sure what is going on. And these are open questions which make you question, is a black hole with a horizon, is a singular black hole with a horizon the right thing to consider in a theory where you have all the resolution you want, or is there something else? So there are two ways to kind of resolve this problem. So one, you could say, okay, you can go into microscopics and you can try to resolve these things and say, okay, now I want to preserve my horizon and my singularity, and maybe there is something that works fine. We haven't got there, but maybe this is the answer. The other option is to say, okay, is it really true that there is a horizon? Because you see, if quantum gravity, the theory that works at the singularity, it gets rid of the singularity somehow, it smooths it out. Then the question is, if you don't have a singularity, do you still need to have a horizon? Right? So if you have a horizon, then yes. So if you have a singularity, then yes, you need to have a horizon. That's at least it's a conjecture which people believe is true. That's just cosmic censorship. But then if you say, if I don't have a singularity, do I still need to retain the horizon? Or is the horizon just some kind of an effective effect that I'm seeing in my classical theory? So I will be taking the second approach to say, okay, what if there is no horizon? Is it a sensible thing to think about? Does it give you any sensible answer? But then as soon as I give you this, your first instinct might be to ask, well, okay, if you don't have a horizon, will whatever objects you're considering, will they actually look like black holes at all? Because you would imagine if your object doesn't have a horizon, it has a surface like a star, it's going to behave very, very differently, right? It's going to have different signatures. It's not going to absorb things you throw on it. So then you would imagine, okay, I can just rule it out directly because it's not going to look like a black hole. Well, people have thought about this problem for maybe more than 20, 25 years by now. And then the answer is, well, you can actually write down objects which are horizonless, and they still mimic black holes very, very well with only very subtle differences. Then if you're phenomenologically motivated, so then you would say, okay, if such solutions exist, then maybe I should look at them seriously and then try to understand how do I distinguish them from a real singular black hole with a horizon. So the whole point of this long-winded motivation that I was trying to give you is that black hole mimickers are not random speculation. There are good reasons to think about them. Again, sorry, I should define. By black hole mimickers, I just mean objects which don't have a horizon. Right? So horizonless objects are black hole mimickers. There is a second class of objects which I was just discussing with Gaurav before the seminar started, which are called regular black holes. which are black holes which don't have a singular, or objects which don't have a singularity but have horizons. So I'm not going to talk about those. Those are a different class of solutions, which Gaurav, Ramesh, and other people in the audience, and probably many more experts have studied in more detail. So I'm going to not talk about that class, which I will call regular black holes. I'm going to talk about black hole mimickers, which is non-singular horizonless objects which can mimic black holes. So that's the purview of my talk. Okay, so let's say you are now inclined, you are motivated by whatever I told you, and then you say, okay, I would like to construct, or I would like to understand such kind of solutions in GR, which are not black holes, but are regular and don't have horizons. Okay, so then you say, how do I construct such a solution? As soon as you try to do it, you are kind of hit by something called Buchdahl's theorem, which is from the 60s. So what this theorem tells you is that if you try to take the simplest possible case, a spherically symmetric object, so no axis symmetry, completely spherically symmetric object made of some kind of ordinary matter. By ordinary, I just mean standard model matter, which is not violating any energy condition. You try to take such an object and you try to see that if you make a ball out of this, which is spherically symmetric, and you try to make it as small as possible, how small can you make it before your theory breaks down? So this is a question that actually Schwarzschild already wondered in his 1918 paper. There is already this solution that exists, but then Buchdahl kind of interpreted it later on and then came up with his own way of understanding it. And the result is the following. If you take ordinary matter and you try to squeeze it as much as you can only do that until a radius of 9m/4, which is like 12% larger than the Schwarzschild radius. So this is bigger than the Schwarzschild radius. And this is called a Buchdahl radius. So the problem is if you try to squeeze it further, then the density goes singular at the center. And so you say, okay, this is not allowed, I can't do it. But in order to get to this, you make a few assumptions. So you are assuming that it's static spherically symmetric. You are assuming that this is an isotropic perfect fluid, which is making this up. This is made of ordinary matter, which doesn't violate energy conditions. The density is either increasing inwards or is constant inwards, but not decreasing. And then you are in GR. So in these assumptions, this is the theorem. But then you say, okay, if I really want to consider an object which is going to mimic a black hole and is made up of, I want to evade this theorem, then clearly you have to violate one of these assumptions, right? So you can't have these assumptions. And of course, people have studied this for decades, and you can choose your favorite one to violate. For instance, you say, okay, you're doing this in static spherically symmetric. That's really not what I see in my universe. Okay, so if you start rotating it or you deform it, then clearly you are outside this theorem, and then you can do fancy things. Or you say, okay, why do you want to consider perfect fluids? I can consider viscous fluids. I can consider multi-fluid configurations. And again, you can break it. You can introduce large anisotropies in the pressure. So radius versus tangential direction could have different pressures. That breaks things. You can put scalars, electromagnetic fields. You can account for matter, which is not ordinary matter, as in you may have motivation for matter which violates some energy condition, etc., etc. So my point is, if you want to make something which is smaller than the Buchdahl radius, which is as big as the Schwarzschild radius, then you have to violate one of these things. And this is the reason why sometimes these objects are called exotic compact objects. So it's the same name for black hole mimickers, and exotic because you're kind of doing exotic things. You're either using exotic matter or you're breaking something to do it. So with this motivation, people have, for the last 20, 25 years, at least, even longer, tried to understand what's going on. How do you construct these objects? What kind of objects can you write down, and so on. So here is my cartoon way of showing you a slice of what these objects look like. So on the x-axis, I have shown the radius of this object in units of Schwarzschild radius. So r over rs equals 1 is when the object is as large as its Schwarzschild radius. Sorry. If r over rs is 3, so r is 6m, this is the ISCO, the innermost stable circular orbit. 3 over 2 is just r equals 3m, so this is the photon sphere for a spherically symmetric object. So these circles or semicircles, I don't know, like sections of a circle are just, so you should think of this as the size of the object, how big the object is. So one of the most well studied and most well understood objects are boson stars. These are solutions which are written down as a scalar field coupled to gravity with some potential, and then depending on how you choose your potential, etc., you can come up with stationary configurations which do certain things. So boson stars are those kind of configurations. They are typically very large and fluffy. So this is a you can think of this as a scalar field which is extending all the way to infinity, but it's mostly peaked around some part, and then you just say, okay, where most of this object lies, that is what I call my star. So it's not really a star. It doesn't have a surface. It's not compact. It's extending all the way out. But this is kind of what people have been calling boson stars. If you consider rotating boson stars, so as you can imagine, if you spin something up, then it wants to come together. So if you have high spins, then you can make them quite compact, but not as compact as the Schwarzschild radius. So you can make them close enough that it kind of sits at its at r equals 3m. But you can also have other fields other than boson. So there are fluid stars where you can start with some kind of fluid configuration which is doing this. People have considered Proca stars where you have massive vector bosons, etc. So you can do a lot of stuff, and people have considered these kind of objects. So all of these, as you will note, are bigger than the Schwarzschild radius, and these are so none of these are motivated from a fundamental theory. So this is like, what can I do? Sorry, I keep clicking. So this is like, what can I do if I want to construct such an object from a bottom up perspective? Right, I want to have some effective theory with some fields, and I want to have this happen. So what can I do? The other side of the story is you may be motivated. Okay, firstly, can I make it as small as a Schwarzschild radius? And secondly, can I have something which is motivated from some fundamental theory that you think for some reason is true? So in the spirit of the latter, there are two solutions which I would like to highlight. One of them are called fuzzballs, and the other, which is a very recent one, are called frozen stars. So fuzzballs are the solutions which are motivated by string theory, which is one theory of quantum gravity that people like. So this again is a solution which is as compact as the Schwarzschild radius and has high energy motivation. The problem is these are, so if you want an explicit solution, these are supersymmetric, and it's hard to write these things down in 4D non-supersymmetric. There is a lot of progress happening there. There are these things called topological stars, which some people are doing, which are attempting to construct fuzzballs in a non-supersymmetric 4D setup, but we are still a long way away from that. Frozen stars are also motivated by string theory. These solutions have come up in the last year, where people are trying to construct something from top-down theory and get something which is as compact as a Schwarzschild radius star. And then Grava stars are again, so okay, so Grava stars are not really motivated from fundamental physics. Like, it's not like you start with quantum gravity and it gives you Grava stars. Grava stars are again a very bottom-up way of doing things. You assume that you want this and that, and then you want to say, what kind of stress tensor do I need to make this happen? And then if you arrange for this stress tensor, somehow you will get this object. These objects, because it's kind of a posteriori, you demand that you want something which is as big as Schwarzschild radius and has certain properties, then you end up with something which gives you exactly that. So using Grava stars, you can also make things which are quite compact. So this is kind of okay.
So when I
Sorry, is
had
there a
a
question?
question, yeah. So
Yes.
these stars like which are like behaving or mimicking like black holes, like is can we like distinguish them using some things, or like for example like quasi-normal modes or something like that? But
Absolutely, absolutely. Right. So this is essentially the rest of my talk. I
oh,
will I will tell you what kind of things you can use and what kind of things have been done. So the
oh,
short answer to your question, right? Right. So this is exactly what my talk is about. So I'll get there. But because you asked, let me just give you a one-line answer to that. If you have something which is compact, as in which has a surface, etc., then you would naturally expect that when you're doing, let's say, collision of these two objects, etc., you would see effects also in the in spiral, because they will have different tidal deformations. They don't have horizons. You'll have different quasi-normal mode amplitudes because they're going to ring down different, etc. It would be very nice if we could actually answer these questions for any of them. The sad reality is none of these models are mature enough that you can ask these questions. The only model where you can ask these questions so far are boson stars.
okay,
And this is because it's a very simple model where you just have a boson, like you just have a phi field coupled to gravity, and that's it. So in this case, people have actually studied effects of collision of these two objects, of mergers, of the remnants, what happens there, quasi-normal modes, etc. And the answer usually is yes, they are quite different. In the quasi-normal modes, for example, there are late modes. So if you just have a horizon, you'll just have the horizon ringing down to stuff. But if you have an interior, which all of these things have, then you can have modes that go into the interior, get refracted, get reflected, come out later. And those will have effects which are completely different from usual black hole horizon. So these are things that people have studied, and I'll tell you why they are not excluded later in the talk. So yeah,
oh,
please ask me again.
sure, sure.
Yeah, sure. Okay. So yeah, so this is a cross section of the kind of objects that exist. There are many more. Obviously, I have chosen a few representative ones, but this is kind of representative of what people have done so far. Okay, so then the question is, okay, given this situation, actually, thank you, God, for asking that, because I'm going to essentially talk about this from now on. So given the motivation that you have these objects, the question is, how would you know that any of these objects is real? So if they existed, what would be a signature for them? So because we live in gravitational wave era, and this is by far the most the or by far this can probe the closest to the horizon of a black hole. So the natural question to ask is, if you had two of these objects which are spiraling around each other and then merging, what kind of differences would I see? So if you had two spiraling black holes, then as we know by now, they will emit gravitational waves, and then you can record these gravitational waves. You can look at the amplitude, the phase, etc. during in spiral. You can look at the quasi-normal modes, which are the ringing modes during the ring down. If you are clever enough, you can start to do things in the merger, but that's still very hard. And then, given all of this information, you can try to understand, do you really have a horizon or don't have a horizon? But in order to do any of this, you need to have a model which you can actually put on a computer and do this, right? So this might sound simple, but it's not. And the problem is the following. You can't just take any random object and evolve it nonlinearly in full numerical relativity. The problem is, if your object is not stable to begin with, when you put it through this merger process, so the in spiral is okay. This is very gentle. You can still do things here. They will pull around each other, do something. But the merger is a highly non-trivial, is a very violent phase during the merger of black holes. So if you have seen simulations of black hole mergers, you might have been surprised. The first time I saw that, I was very surprised. That so if you look at the horizons during merger, they don't. I mean, there is no hair theorem anymore, right? It's a very dynamical space-time. The horizon is being distorted in every possible way, and things are happening very violently. So in order for any object to survive all of this and to give you something at the end, the object has to be stable at a nonlinear level, right? It's not enough to just prove linear stability. So linear stability is okay in this phase, but you cannot get to that phase. So then the question is, okay, are any of these objects non-linearly stable, or do we understand at least how they behave? If you ask that question, as I was telling Gaurav, the only solution that so far has proven to be non-linearly stable is a boson star. And the reason is, again, firstly, it's a simple enough system that you can actually study it in full detail, but also because these solutions have existed since the 70s. So people have had a large amount of time to think about it and to understand the different properties of it and to work through it. So given that we have so many models, but it's very hard to answer this question of nonlinear stability. And so this is a prerequisite in order to actually take things and start merging them and then understand what is happening. So in order to get anything real, we would like to have things which satisfy this criteria, and many more criteria. So with this motivation, the question that I started asking along with my collaborators many years ago is, can we actually come up with a model which is motivated from high energy, just because of my personal taste? I would like something which is motivated from high energy physics and not a pure bottom-up model, but then which is also concrete enough that you can actually ask these questions. So there are two ways of approaching this field. One approach in understanding black hole mimickers is, okay, I don't need to construct a concrete model. Just give me some generic model, and I will try to understand things at a linear level. People have done that. That's a very productive approach. But then, given the fact that we can now explore nonlinear dynamics using gravitational waves, etc., I think the other side of the question, which has not been answered so far, is, can you take whatever model you want, but can you take a model and then work it out all the way to the end and show me what is the prediction, what should happen if this was a real object in the sky? And this, I think, is very important, because if you want to compare things with data, as we have more and more data coming in the next few years, it's productive to take this approach. Because if you don't do that, then you can always keep doing things in an approximation, and this may or may not represent what is happening in nature. So with this motivation, we started working on, so we constructed a model, which I'll explain in the next few slides. So we call them ADS black shells for reasons which will become obvious. So this is a model which comes from high energy physics and is concrete enough that you can actually answer these questions. And I will show you in the next 30 minutes some of the questions we have answered, what the outcome is, and then what kind of things remain, and what are the outstanding questions that need to be answered. So one thing which I would like to point out here is, you see these ADS black shells, these objects I will talk about, are actually not as small as Schwarzschild and not as big as the photon ring, but they sit somewhere in between. And this 9/8 times the Schwarzschild radius is exactly the Bogdal. That's 9/4m. So these objects naturally sit at Bogdal radius for reasons which will become clear in a second. Okay, so before going on, let me give you a little bit of a history of this thing. So this is something that I've been working on with some of my fantastic collaborators here. We have been working on different aspects of it over the years, with the last work which we did last year, and then there is still there's a lot of ongoing work, and I'll tell you what they are. So this is in collaboration with Ulf Danielsson, with whom I did my PhD many years ago. He's a professor at Uppsala University in Sweden. Giuseppe, who is a professor in Rome. Louis Lerner, who is a professor at Perimeter Institute, and Franz Pretorius, who is a professor at Princeton University. So together we've been exploring various aspects of it, trying to figure things out as we go. And yeah, let me try to give you a snapshot of what this thing is about. So what is this ATS black shell object? So this is essentially this is a horizonless endpoint of gravitational collapse, and this is inspired by the theory of quantum gravity that I am most familiar with, which is string theory. So the way it works is the following: you have a collapsing shell of matter, and if you just had GR and none of these effects, you would just expect to form a black hole. But what this is telling you is, no, you have another possibility where you don't form a black hole, but you form something else. So this is a vacuum bubble. I'll explain in the next slide what that means. So what you should think about is this: if you have a collapsing shell of matter, there is some mechanism motivated by high energy physics, which tells you that instead of forming a black hole, you might form something like a soap bubble. Essentially, it's a vacuum bubble. It has anti-de Sitter space inside, and the outside looks like regular space-time. So this thing is going to nucleate out of vacuum, and this object, with all its properties that it's going to inherit, is what is meant by the ATS black shell. So it's a shell-like object, literally like a soap bubble, which has a different vacuum inside than outside. And the difference in this vacuum inside and outside is compensated by some stress tensor which sits on the surface. So that's the big picture. And now let me give you a bit more detail of where does this object come from and how you should think about it. So if you're familiar with Coleman-DeLucia tunneling, for example, in QFT, so this is very, very similar. So imagine that you live in a vacuum, which is Minkowski, but then there is, so in the full theory of your vacuum, imagine that you have another, so imagine that the Minkowski you live in 4 dimension is the metastable vacuum, and there's a more stable anti-de Sitter vacuum somewhere else. When you tunnel from this Minkowski to this anti-de Sitter vacuum, you can do this via, let's say, gravitational instanton. Then you would expect the instanton, so this is a domain wall which is taking you from one vacuum to the other, and in the limit where this domain wall is thin enough, you can imagine that this is going to look something like the soap bubble which I showed you. So this is the cartoon picture. If you go into a bit more detail, you can say that, okay, instead of just having an empty gravitational instanton, which is not really made of anything, it's just an interpolating domain wall, you can also have sources. So there is the seminal work by Brown and Teitelbaum from the late 80s, where so this paper was called neutralization of the cosmological constant by brain nucleation. So what they were considering is, imagine you have a theory where the cosmological constant is given by the expectation value of some field. So F, you should think of F as a two form as an example, but I mean, it doesn't have to be two form, it can be anything else. So there's some gauge field whose field strength is F, for example. There is an object in your theory which is sourcing this field strength. So this is like a charged object, and the F is the field strength of that charge. So if you nucleate such an object by this vacuum nucleation process, then you're going to source a jump in the flux across it, obviously, because this is charged. So if you have some flux on one side plus the charge, this should be equal to the other. So in this way, if you had F as your initial vacuum expectation value everywhere in the universe, and you nucleated something which had a charge delta F, you can show that by the same arguments as Coleman-DeLucia, that the most probable configuration where you have SO3 symmetry, and then you should form a spherical bubble. And inside the bubble, the value of this field is going to be reduced by this amount delta F. That's exactly the charge of this object. So from here, you can already see that if you form such a thing, you will have a difference in cosmological. So if F was contributing to cosmological constant, you will have a difference in the cosmological constant inside and outside. So if you run with this idea and then you try to make this more rigorous and concrete, and then you try to calculate what happens and can you arrange for such a setup in a theory of quantum gravity that we understand. And in our case, it was a string theory because we were most familiar with that. So then you start with this, you write down a concrete setup where you can make this happen. And then you realize that, yes, you can actually form vacuum bubbles, which take you from one cosmological constant to the other. In particular, if you start with Minkowski 4 as the vacuum we live in, you can go down to anti-de Sitter vacuum, also in 4 dimensions. And then the wall, which is the bubble wall, which is carrying out this transition, is going to end up with certain properties. And these properties are not negotiable, as in it's a prediction that comes from string theory if you start from there. And it tells you exactly what this bubble wall should be made of. So before doing any kind of gravity, if you just ask this question purely from a quantum theory, from a quantum gravity theory, saying, okay, I want this to happen. I want Minkowski 4 to go to ADS 4 via a bubble nucleation. What does it predict for the stress tensor that should sit on the surface of this brane? And the answer is the following. String theory tells you that this object should be made up of three different kinds of perfect fluids. One of them should have an equation of state, which looks like this, P equals minus rho. And this is exactly the equation of state of the tension of these things called D branes, which exist in string theory. So these are just membranes which have charge. It tells you that you should have something which goes as the equation of state of radiation in 2+1 dimensions. So it's P equals rho over 2. And then some subleading piece, which should go as stiff matter, where P equals rho. So before doing any GR, just from a high energy perspective, if this were to happen, you would indeed get Schwarzschild metric outside. You would get some, so lambda is the cosmological constant. You would get some anti-de Sitter space inside, and the surface of this bubble is going to carry whatever stress tensor has to make this happen, and that is going to be made up of these three pieces. So okay, so you say, okay, this is what string theory tells us, fine, but we don't live in a supersymmetric whatever universe. We live in our real universe in 4D, and then you should really ask the question to gravity. What does gravity tell us should happen? So then you say, okay, if such a thing were to happen in gravity, so forget everything about high energy, and I want Schwarzschild outside and ADS inside, then of course I know that junction conditions should tell me what's going on, right? So Israel junction condition just tell you that if you have one space time, so imagine you don't have this bubble and you just had Schwarzschild, then of course it's a vacuum solution. You have ADS, this is the vacuum solution with a cosmological constant. But now if I take a space-time, which is the patchwork of both of these, I have this and somewhere discontinuously changes to that, then the junction conditions will just tell me what kind of stress tensor has to sit on the surface in order to make this whole thing a solution of Einstein's equation. And that's just this. This is the first and the second junction condition. So this Sij, which is given in terms of the jump of the extrinsic curvature, is going to tell you exactly what I told you. So then you ask this question to GR independently of any string theory. And then, to your great surprise, you find that it gives you the exact same answer. So it does tell you that you need to have a tension of a brane. You need to have something that looks like radiation and stiff matter. So the model that you are constructing in string theory, this is actually realizable in gravity. And this gives you confidence. Okay, so the kind of stress tensor that you need to form this is not some random object that you just cook up, but this is actually what is required also from the high energy side. And then you say, okay, putting these two things together, yes, I can form such a bubble by writing down such a theory, and this is going to give me what I want. Very good. So you start from there, and then you say, okay, given that I can form such an object, what are the because like I told you, from the string theory side, you don't have an option of turning things on or off. This is what you get. Then you say, okay, if things are already determined, does it also tell me anything about the object? How big is the object? What's going to happen, etc. So when you do the math, you figure out that the size of this object, given these restrictions, is already fixed, and it sits at the Booktal radius, and you have no way of changing it. So you are getting something which looks like a vacuum bubble of anti-de Sitter for inside Schwarzschild, whose size is fixed to be 9m over 4. Then you say, okay, interesting. I can get this object, but then because it's bigger than the Schwarzschild radius, so this might have consequences. Maybe it's not going to look like a black hole. Let's see what we can do with it. So given the motivation that I gave you a couple of slides ago, that one of the most important things to understand whenever you propose anything to replace a black hole is how stable is it? If I throw something at it, is it going to remain there or is it going to disintegrate? Right? And this is important because if you try to do mergers with them, they will have a lot of violence, and you want to ensure that it survives that violence. So then you start wondering about, okay, let's study stability of this. So firstly, let's study linear stability, and then we go to nonlinear. So one cheap way of studying linear stability is just to write down the junction conditions as a dynamical thing in the radius. So you say the radius is a function of time. So you just write down the usual junction conditions. You can rewrite it as some kind of evolution equation, a kinetic equation on the radius. And from here, it's very easy to see that a static solution that I showed you before, an instantaneous solution that I showed you before is going to be unstable. So it essentially sits on top of a hill and it can roll down the hill very easily. So generically, any solution of this sort is unstable. And this is a generic problem for any thin shell model. If you have worked with gravastars, you will be very familiar with this problem. It's always the same. It's an unstable solution. However, this is not the whole story for the specific thing that I showed you before. So you remember I told you that the stress tensor on this surface is not a single fluid. It's made up of three different fluid components. right? So when you write down the equations of motion, you also have a continuity equation, right? You have to ensure that the fluid on the surface satisfies continuity equation. If you write that down, essentially what it tells you is that some quantity like this, A plus B plus C, should be equal to 0. If you had a single fluid, what is usually done is you set the whole thing to be 0. But because you have three different fluids, what you will see is that they exchange energy between them. So the tension component, which is, you can think of it just as the physical tension of a brain, of a membrane, and then the radiation on top of it, they're exchanging energy between each other. And then the other one is also, but this is subleading, so you can forget this for the moment. So as soon as you put these microscopics into the picture and you try to understand, okay, what is the energy flux going between them? So these don't have to be 0 individually, but the sum has to be 0. So each of them, so for example, the brain tension can give you pumped energy into the radiation, which is a gas, and then the radiation can essentially steal energy from it. And when you put this mechanism so when you put this effect into your calculation, you see that indeed you can get radial stability. And this we realized very early on. But then the big question is it nonlinearly stable as well? So this is a very, very hard question for a variety of reasons. Firstly, whenever you write down any solution, let's say any mimicker that you want to write down, to frame this question, you will first need to make sure that the equations that you're getting are well posed. Well posed in the sense of a partial differential equation. If you don't have a well posed set of PD, then the solutions you get are not very meaningful. So you have to ensure that you get well posed equations, and then you have to impose the appropriate boundary conditions to find a solution to this. Surprisingly, this has never been done for anything else other than boson stars, like I mentioned, because boson stars are a different class of solutions. So the first example of this that was ever done for a mimicker was for these ADS shells, and this was done numerically by Franz Pretorius, Lewis, and Ulf. So, and the answer is yes, they do turn out to be stable. So the only thing that has been, the aspect that has been studied so far is radial stability, and non-radial stability is what we are studying right now at the moment. And the reason for radial is it's already very, very complicated to do it for the radial one. So that's the first thing you do. And if it turns out to be stable, you do the second one. So let me give you a cartoon of what they studied in this. So here, this picture here, modulo these cartoons that I drew on top, is a plot from that paper.
Suvendu,
Sorry, was there a question?
question? Yeah. So
Yes.
in one of the previous slides where you're talking about this tunneling thing, the old works of this Coleman and this thing, so they described it by going in a Euclidean this thing.
Right.
So if you go in a Euclidean path integral, blah 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 blah, and then
Right.
basically there's a spherical shell. Basically, that topology is the most dominant one, and that comes
Yes.
out as basically a spherical shell kind of a thing. So,
Yes.
you're also doing it in the same way, basically in the going in the Euclidean and then finding the what is the most dominant contribution.
Right. So going to Euclidean is just to find the instanton, right? So
Right.
the instanton is just it's just a positive energy solution to the Euclidean action. So to find the Euclidean action, so in order to find the instanton solution, you go to Euclidean frame, solve your equation of motion. But once the shell nucleates, then it evolves in Lorentzian time. So if you have seen these pictures of black cigars, I think they're usually called. So you form like so if you're drawing a Penrose diagram of this thing, what you will see is so at time t is 0. So this t is then it's the same for Euclidean and Lorentzian, because at t is 0, t is same as I tau. So at time t is 0, you will form this shell, which in the Penrose diagram would be like a hemisphere, half a hemisphere, a hemisphere. And then once it's formed, then the evolution happens in Lorentzian time, and then you will see this thing that it starts to accelerate, and you get these funnel-like pictures, and this is what people usually call a black cigar. Yeah. So right, absolutely. So in order to find this solution, you have to go to the Euclidean frame to recover what is your instanton. But this is just, I mean, this process is just to find the initial condition, and once you form the initial condition, then it will expand. It will accelerate in Lorentzian time.
Okay.
Yeah.
This will also still have like one negative eigenmode also
Yes. So right. Exactly. So the negative eigenmode is just telling you that once you form it, it's going to expand. It's not going to stay there.
Right.
Yeah. Yes.
Okay.
Absolutely. It's the same thing. Yes.
Yeah. Thanks.
All right. Yeah. Thanks. Okay. So right. So what they did is the following. They took the ADS black shell, which is right. So okay. So the x-axis here is time. The y-axis is the radius of the object in units of mass perturbation. So what they did is the following. So they took the ADS shell, And then they wanted to check for nonlinear stability. So how do you do it? You take the shell and you essentially hit it with more matter. So in this case, this was like you throw some extra matter on top of it and you see what happens, how the shell reacts. So what happens is when you throw some extra matter on it, obviously you would expect that the shell is going to absorb it and it's going to, wiggle around, grow, etc. So then you see that, yes, so the radius, which was, so if it's on the baseline, then it means that you have the ADS black shell. If it's away from the baseline, then it means that it's perturbed. So you hit it once, and then you see, yes, the shell gets perturbed, and then as time goes on, it wants to come back to where it started from. So it's coming back, coming back, coming back, coming back here. If you don't do anything, it's going to just come back and then become the shell. But then you say, wait, I want to make it as difficult as possible for the shell to be stable, right? If you're doing calculation like this is kind of the right approach. You don't just want to do the simplest thing, you want to make it as hard as possible. So then say, okay, let's hit it again. So again, at this point, you give it another big shock. You throw some more matter on, and then you see again the shell again gets disturbed, does whatever it wants to do, and then you let it settle down, and then eventually it comes back to this point. So this is like one of the, I don't know, it's a very nice picture which tells you already without looking at any calculation that yes, this object with these properties of energy exchange, etc., is going to be non-linearly stable against these kind of perturbations if you do this. Okay, so given the fact that we now have an object which is stable, at least in the regime that we have studied so far, it makes sense to then ask more real questions. Okay, you have an object which is motivated by high energy, gives you well-posed equations of motion, and is non-linearly stable. Can it represent anything real, right? So spherically symmetric objects are not real in nature, as in a Schwarzschild black hole is not a real object in nature, right? If I throw one particle which is off shell, it's going to start to rotate. So clearly it's not a real object in nature. Real objects in nature are supposed to be rotating. So then you say, okay, can you make a rotating object which looks like this, has the same properties, and what are the consequences? And this is important if you want to understand real world properties of these objects and how would you distinguish them. Okay, so rotating mimickers are always problematic. And the reason is the following. If you have a non-rotating object, a spherically symmetric object, then it doesn't matter whether or not you have a horizon. The metric outside is Schwarzschild. That's just Birkhoff's theorem, right? But if you have something that is rotating, it's axisymmetric, then this is no longer the case. If you have a horizon, then the metric is curved for sure. If you don't have horizon, the metric does not have to be curved. So this is very different from having a spherically symmetric object. Okay, so what do I mean by curve versus non-curve? So if you write down the multiple expansion, so given any object, I can kind of describe the shape of the object as a series of multiple moments, right? If it's a complete sphere, it's doing nothing, it's completely round, then it just has a mass, and that's it. But for example, curve is not a sphere, it's oblate. So because it's oblate, so you have the mass, of course, but then you also have some shape which is telling you how oblate it is, and that is the quadrupole moment, which is this m subscript 2. But in principle, you can write down an infinite series of moments. So given any object, I can write down the mass, which is the monopole, the quadrupole, the octupole, the hexadecapole, and so on. So curve is a very, very special geometry in that all of the higher multiple moments are dependent on just the mass and the spin. So the quadrupole moment depends on the spin, m0 depends on the mass, and everything else is a function of these two parameters. This is essentially the no-head theorem if you don't include charge. But if you don't have a curved black hole, if you have some general non-curved solution, so imagine the metric outside the Earth or the metric outside a neutron star, that's clearly not curved because you don't have a horizon and you are rotating. So in all of these cases, you can do a multipolar expansion of the space-time and you're going to get some zero moment, which is the mass, some quadrupole, some octupole, etc. And they're going to be all independent numbers. They're not going to depend on each other, right? So if you don't have a horizon, as is the case for a mimicker, the metric does not have to be curved. Right? The metric is something completely different. And then the question is, what is this metric and how do you find it? I mean, it's a much harder question than doing it for the spherically symmetric, because there at least you have Schwarzschild, and then you can work from there. In this case, you don't even know what the metric is outside. So this is a problem that people have faced time and again when you want to consider this. And usually the approach that is taken, which I do not like, is to just assume that the metric outside is curved. You can do that, but there is no reason for it. I mean, curve is one special solution in a huge family of generalized solutions. And why would you pick that one special solution, right? So, right. So when I was working on these rotating black shells, we had to face the same question again when we wanted to construct a rotating black shell. And the question is, what is the metric? Thankfully, because of the way these objects come about, so there is a high energy motivation and there is a physics which tells you exactly what the object is. You can actually work it out. And then it turns out that the metric outside is determined uniquely, and it's not curved. So there is no freedom in telling you, like, it's not like you assume the metric is this and you give it that. You just work out the problem from first principles and you end up with a metric, and it is what it is. So this is the calculation that I did perturbatively in spin, and I only went to spin 8 to the 6, which was already messy enough. So in principle, you can keep going as long as you want. I ran out of energy after 8 to the 6, so I stopped there. So in principle, you can construct the metric outside a rotating ADS shell to arbitrary orders in spin. And what you will see is that the different multipole moments are all different from curve. So as an example, if you do spin of a half, let's say, the quadrupole moment is about 1% different from curve, so it's very close. And then the next multipole moment is about 10% different, and then so on. So the point is, a rotating ADS black shell has a unique metric, which is outside and is given by some quantifiable numbers. And then if you say, okay, qualitatively, what's going to happen with the shell? What happens when it rotates? So when it's not rotating, it's perfectly spherical. As you rotate it, so for instance, if you go between Schwarzschild and Kerr, Schwarzschild is perfectly spherical, the horizon. As you start to rotate it and it becomes Kerr, the poles shrink closer to the center and the equator gets fatter. So this is an oblate shape. If you try to do the same thing with ADS shell, you start with the spherical one, which is non-rotating, and then you start rotating. It does exactly the same thing. It also becomes oblate, but then it becomes oblate in a slightly different way than curve. And that is what these numbers are telling you. How is the shape of this thing different from curve? And you can quantify this by writing down what the multipoles are. What is even more interesting is the following. Like I told you before, there are different kinds of fluids which are making up the stuff that lives on the surface of this object. So if you then try to understand what is this fluid doing, is it flowing, what's going on, then you will realize that there is a matter component which is flowing, and then there is a heat component which is compensating it. So okay, let me just I realize, sorry, how long do I have? I think I'm running out of time.
So maybe like 10 minutes or yeah.
Okay. Okay, I'll try to be quick. I realized
15 minutes we can
Okay,
have.
perfect. Thank you. Thank you. Yes. I'll try to hurry up. Okay, so let me just explain this picture, and then I'll try to hurry up on the next one. So what this picture is showing you is the following. So I told you you have these radiation fluid which lives on the brain. So if the object was not rotating, then the radiation fluid would just be sitting on this on the shell in some way. As the object starts to rotate, so here the axis of rotation is vertical, and it's rotating what is this, clockwise, if you see from the top. So as the shell rotates, it's going to drag the fluid that is sitting on top. And these arrows are so this is not a cartoon. It's literally the vector field plotted on a sphere. So you can see that the fluid, the radiation fluid, which is the matter component, is being dragged along the flow. So it's essentially going in the same direction, and then it's gravitating towards the poles on either side. And then because you have to satisfy continuity equations on the sphere, etc., then you're in the regime of relativistic hydrodynamics when you study this. And then you will essentially conclude that there is a heat flow which is compensating it. So the equators are hotter, sorry, the poles are hotter than the equator, and then heat is flowing from the pole towards the equator. So this is kind of like trade winds so if you look at how winds work on Earth, so the sun heats up the equator more than the poles. So there is heat transfer from the equator towards the pole, right? Heat is going that way. And then because you have hot air, which is kind of going there, and the Earth is rotating, you would get exactly a picture like this in the matter flow, but in the reverse. So it was very curious that essentially you have the same kind of viscous drag and things happening when you are studying a realistic system, which is doing these kind of things. Okay, anyway, I don't want to go into more detail, but please ask me if you have questions about this. Okay, so given all of that, let me now come to the more interesting part of this work, which is, okay, so you have a candidate, you have something which you can write down from first principles, you understand it well enough, you can write down rotating solutions, there are visible differences from Kerr. And the question is, how do you distinguish this from Kerr in a real experiment, right? This was the whole motivation where I started from. I want things to be distinguishable from a real experiment. And the reason is not because I believe that this is what happens in nature and I am kind of, I'm dying to make an ADS shell to be the real thing in the world. The motivation is to actually ask the question, if you could take one model and then work it out all the way, would you learn something from this model? If it turns out to be the theory of the universe, okay, then you are very lucky. But more often than not, it's not be the real theory of the universe, but you will have learned something along. And the question is, how far can you push this calculation to make connection with real experiments? And what does it tell you about future models that you would like to understand, or how should you approach this problem? So that's kind of my perspective. So, like I said, there are two things. There are two kinds of observations that we have access to at the present time. One of them is electromagnetic, and the other is gravitational. So let me start with electromagnetic observations. So here I will show you a simulation. Let me pause this for a second. So what you're going to see here is this grid here in the background. This is just space-time curvature. This is represented like that. This black thing with the red circle around it is a black hole. This thing on this rectangle on the right hand side is your observer screen. So this is my camera, and what you will see is photons coming in from different places, and they are going to get lensed by this object in the center, and then they're going to end up on the screen. You will see a number on the left, which is n. So n just counts how many times does this photon orbit around the object. If it just lenses directly, it's n equals 0. If it does half a circle, it's n equals 1. If it does one full circle, it's n equals 2, and so on. Okay, so let me play this video. So here you see photons which came directly and did not turn around. So they just came, they got lensed with 0 rotations. And this is supposed to be light that is being lensed by a black hole or any compact object. But then you will also have photons which are turning around once, right? So these are the n equals 1 photon. And when you collect enough of these photons, as you see here, you will also get some image, which is a lensed image of whatever you had seen. And this is going to be a thinner band. But then you can keep going. You will also have photons which will turn around twice. For example, the one you just saw. And then when you wait long enough, you will see them on your screen as giving an even tighter image. So what is happening in nature, because you have light coming from everywhere, is all of this is happening at the same time, right? So you are going to have n equals 0, 1, 2, etc. photons, and the entire image is what you're going to see if you actually had a telescope and you looked into a black hole from far, right? So this simulation is done by some colleagues of mine. Wait, hold on, I think I have. So yeah, it's done by these colleagues here. Sorry, I was under my mouse cursor. So this image, this image here is the final image that I showed you on the previous slide, and this is made up of these n equals 0 ring, n equals 1 ring, n equals 2 ring, and so on. So one thing to realize is as you keep going to higher n's, these rings keep becoming thinner, and you're superimposing them. So this n equals 2, n equals 2, n equals 3, and so on. So the place where you keep adding them, like the place where you keep superimposing them more and more, is the one that is going to get brightest in the image, right? So you have this, you add this is brighter, and then you add this, that is brighter, and so on. So in the final image, you're going to see a very bright ring, and that bright ring is supposed to be the photon ring. So this is where, if you didn't do any of this calculation, you just computed what is the orbit of a photon, which can just keep circling around this object forever, that would be the photon ring. So that's the brightest feature in this image. So here I have done a GRMHD calculation, and then here I show you a GRMHD, the result of a GRMHD calculation, where you can see that this bright ring here is the photon ring, and then inside you have all of these objects. And then just to orient you to the picture I'm going to show you on the next slide, you have a few different features on this object that I want you to see. So one is the photon ring, which is the brightest object. But then you see from the photon ring inward, it's not all black. You still have features inside, right? So these are the photons which are escaping. These are the photons which are escaping from the horizon, and they're coming back to you. So the inner shadow here, this is a direct image of the horizon of the object, or the black surface. And then in between here, you still have stuff. And then you have a bright ring, which is a photon ring. So these are the kind of images that the EHT is looking at right now, except that it's a bit blurry because you don't have enough resolution, and there is astrophysics that we don't very well understand. Okay, so now I will show you results of these calculations for curved black hole versus the ADS black shell. And like I showed you before, the multipoles are different. So you would expect slight differences in these things. And the question is, what are the differences? How quantifiable is it? And how should it look for an EHT observation? So here I have showed, so these pictures are for the curved black hole. So the blue line here in both of these pictures are the photon ring. The black thing here with the white circle is the inner is the inner shadow. This is an image of the horizon that I showed you before. One way to characterize these pictures is by drawing these curves. So because I don't have time, so let me not get that. Let's just look at these pictures. So this is for a spin of a half, and these two images differ in the observer inclination. If you're looking at it more towards the pole or more from the equator, then they're going to look slightly more deformed. If you do the same calculation for the ADS black shell, which is now shown with these dotted lines, so the solid lines are still Kerr and the dotted lines are the ADS shell. So you see two differences. Firstly, the inner shadow is bigger for the dotted line. And that is because, like I said, the surface of the object doesn't sit at the Schwarzschild radius, but is sitting outside. So clearly, as you would imagine, the photons, the last photon that can go inside cannot touch the horizon, but it has to stop at the surface, which is why you get this difference. And the second difference is this blue line, which was there before, is now superseded by this red dotted line. Okay, it's very hard to see in this picture, but if you do these, if you plot this projected diameter, which is observable for EHT, then you'll see a difference. So there are two differences. The shape of the photon ring is slightly different, and the size of the inner shadow is slightly different. And these are quantifiable things that you would expect to then see in an observation if you had the resolution to look at this. Okay, and let me tell you the very last thing, and then I'll stop. Which is okay. So this was electromagnetism, and the question is, what happens when you're looking at gravitational waves? How does what kind of effects would you see? So a gravitational wave again has three phases roughly. You have the inspiral phase where things are very far from each other and they're kind of getting close. You have the merger, which is a very violent nonlinear process where things are merging. And then once you have formed the common horizon, it's going to ring down to form your final object, the spherical horizon, or in this case, axisymmetric. And this is the ring down phase. And the question is, what kind of effects would you expect to be different and how do you calculate them? So the merger has to be treated completely non-linearly. This is something which is, and numerically, which is very hard and has not been done. But for the inspiral and ring down, there are things which you can compute right now, which we have computed, which will show you differences. So in the inspiral phase, the way you organize things are by one way to organize things is by using a post-Newtonian expansion, which is to tell you what is the orbital velocity of the objects as a function of time. So when the objects start far from each other, the orbital velocity is very slow. As they get closer to each other, the speed increases and this v over c keeps increasing. So then if you have effects which show up at lower post-Newtonian order, then these are going to be more pronounced than things which appear at higher post. So post-Newtonian just means what power of velocity does it appear. So at lowest order in this post-Newtonian parameters are the spin multiples. So these are going to be the most obvious things which you can detect and inspire. And this is exactly what LIGO-Virgo-Kagra collaboration is looking at. So they are actively looking for deviations of spin multiples from Kerr, etc. So this is this is a v to the 4 effect. So this is called a 2pn effect. So as I showed you, the spin multiples are different from Kerr, and this will show up here. It will show up in a difference in the phase of this wave. And then there are tidal love numbers, which essentially tell you how deformable is the horizon of the object. So a black hole in 4D GR has zero tidal love number, meaning that if you put in a tidal field and you try to pull on it, the horizon is rigid. It doesn't deform. But if you don't have a horizon, but you have these ADS black shells, for example, or a neutron star, then the horizon can deform and it will give you non-zero tidal love numbers. On the other side, if you look at the ring down, then there are these things called quasi-normal modes, which Gaurav asked about before. So this is exactly when the object is ringing down, it's settling down to its final form, it's going to emit different frequencies of waves, and then the amplitudes are going to be something. And then those are also going to be different. So I will show you in particular, or I will flash very quickly, the results for the tidal love number and the quasi-normal modes. So for the tidal love number, again, okay, let me not go into detail. Let me just, again, tell you that if you have two of these objects going around each other, because the tidal deformability for black holes is zero, but for non-black holes is not zero. So you would expect that the fact that this guy is pulling on this guy gravitationally is going to give you some small changes in the gravitational waveform. And the question is, how big is the change and how do you see it? So once, okay, so please ignore all this because I'm running out of time. Let me just give you the final answer. So once you go through all the calculation, what you realize is that the tidal love number is non-zero as you had expected, but it's a very, very, very small effect. So to compare, if you had a neutron star of the same mass, the tidal love number for these black shells would be 3 orders of magnitude smaller than that. So in principle, yes, there is an effect, but it's a very, very small effect. And then going back to the quasi-normal modes. So again, these are ringing modes of the object. There are two ways to understand these quasi-normal modes. Either you can do it fully non-linearly and then understand it, which is something we have not done yet. But the other way is to do it in the high frequency limit, which is called the iconal limit. And in that case, things become simpler because then everything can be written down in terms of photon geodesics. So you can do that analysis, and this is the result. So you can just look at the central plot here. This omega c is going to give you kind of the real part of the quasi-normal mode. Again, each of these lines is made up of two lines. There is a blue line, blue solid line, which is Kerr, and then the red dashed line, which is the ADS shell. And you see that they are different, but they're very, very close. It's less than 0.5% different. And then you have two different modes. You have the co-rotating and the counter-rotating orbit. So those are the two different branches. And for all of them, you still have a difference for sure, but it's a very, very small difference. Okay, so let me try to conclude. So what I've told you so far is that in order to understand black hole mimickers, the big problem which still exists is that no black hole mimicker is mature enough to actually study everything that you want to study. The closest we have come is with these ADS black shells, where we have started to understand questions about nonlinear stability and have tried to make a connection between the theory and the observations. So this problem, if you're interested in it, has two parts. You have to write down a theory, which is, you have to write down some for my taste, you should write down something which is top down, which has top down motivation, but it depends if you want to start with bottom up. But in any case, you should have some effective classical theory which you can describe. And then from that theory, you need to connect things to observations. So there are two different camps of observation: gravitational waves and electromagnetism. And then depending on how far your model has come, you'd be able to answer one or the other. So the kind of things we have answered are questions about stability. In the observational side from gravitational waves, I showed you about tidal deformations, quasi-normal modes, spin multipoles, etc. On the electromagnetic side, we have done lensing bands, photon rings, electromagnetic properties. So this I did not talk about today, but we've done a lot of work on that. At the moment, I'm working on tidal heating as well, which is a different effect that we can talk about if you want. And also on the accretion and GRMHD side, which is the very realistic way of looking at how things work. And then question about jet production, etc., which are relevant for real world. And then in the middle, there is a bunch of stuff which I'm also thinking about. So again, happy to talk about any of this stuff. And then the last thing I would like to tell you is that the point of doing this work is not just to work on one single model, but also to figure out universal properties that every mimicker would have. And this is also some work which is ongoing with some people. So I can tell you more about that. All right. So thank you for your attention, and sorry for going over time. Very happy to take questions.
Thank you, Suvendu, for the nice talk, and it's very exciting to hear about this. So now the panel, platform is open for audience to like ask questions. So in the meantime, maybe I can ask few things.
Yes, please.
So so these objects that you have, so which are basically like internally, like they are basically ADS this thing, and outside is a Schwarzschild black hole, Schwarzschild kind of a geometry.
Yes.
And so these are like, as I understand, so these are like stable solutions, which are like quite stable actually to perturbations, and even nonlinearly stable.
Yes. So they're
So,
nonlinearly stable to radial perturbations. That is the side we have been able to study. There
uh-huh.
is always a question of what happens when you do non-radial perturbations, which is what we are studying at the moment.
Okay.
So right. So if you have a non-rotating object, you have Schwarzschild outside and ADS inside. If you have a rotating object, then the metric outside is this non-curved generalized metric, and you have ADS inside. So in principle, what you want to study is stability for every single one of them. So you want to so you want to do stability for the non-rotating one, which is the one that we are doing now, because that
Yeah.
is, it's you approach it in steps.
Uh,
And then the real one would be the rotating one,
mm,
and the real stability would be non-radial stability of a rotating ADS black shell,
mm,
which is like the final problem that you want to answer.
mm,
So we are still a long way from there, which is why I would not say that everything has been solved. What we have done is the first non-trivial step, which is to show radial stability of the non-rotating one. So the non-linear radial stability of the Schwarzschild one, which is the one which has been done.
but this
So
kind
we
of
are taking the next.
would have happened if there was a transition happening from one vector to the other one. So,
Correct.
I see, I see.
Yes, yes,
Okay,
yeah.
okay.
So the way you form these objects, so the formation mechanism is a vacuum tunneling. So the
It-
space time that you're living in is going to tunnel into something more stable.
mm,
That's the formation channel.
mm,
Yes,
mm, mm.
yeah.
I
I mean,
see.
whenever you have a model for a mimicker, or whenever you study mimickers, you kind of have to answer a few of these questions, right? How does this object form? Once it forms, does it stay there? Like if it accretes matter, or if it gets hit by something, does it stay as it is, or does it collapse into a black hole? And then once you have answered those questions, then you go forward and you say, okay, now if I take two of these objects and collide them with each other, how does a gravitational wave look like? Right. So you have to answer them in steps. And we have kind of done the first step, part of the second step, and part of the third step. And then we are kind of filling in the rest of it.
Uh, but I guess there might be also like primordial ones which might be there in the early universe, which might have formed because of transitions happening and
Yes. This right. So this is an interesting question which I have not thought much about. Yes. I think the formation mechanism would still be similar. You would still have some kind of a vacuum tunneling, but
mm,
then right, the fields responsible for the tunneling would be very different in a primordial black hole versus
oh,
a late
I
time
see,
black hole.
I see.
Yeah, yeah, but I haven't thought much about primordial black holes, to be honest.
Okay. Okay. Yeah. Let's see if there are any more questions. So as of now, I don't see any raised hands. So I guess if there is no further questions, we can maybe just conclude the talk and stop the recording. So if the audience doesn't see have any further questions, then maybe we can thank the speaker and for the nice, wonderful talk and giving a presentation at such a, I think it's very early in the morning for him. So that yeah, so sorry for the inconvenience, but thank you for accepting to give a talk. And yeah, it was wonderful to hear about these black hole mimickers. It's a very exciting thing,
Thank you very much.
and
Yeah,
yeah, it's wonderful to learn about it. That there are so exotic things happening also. Thanks very much. So I'll take
yes,
if I have some more things to ask, maybe I'll write to you at some point of time.
perfect. Thank
Yeah.
you so much. I'm very happy to give this talk. No inconvenience at all. Thank
Uh,
you.
thank you, Savendra. Thank you. So I'll stop the recording
Thanks.
now.